Thank you and welcome everybody. I hope that you're ready to get learn about 2022. ASHRAE 90.1 2022 is a very different ASHRAE publication than in the past. I've been working on I'll go to that slide. We'll just start off because we're going to spend 2 days together and I'm going to try to give you as much information as I can. And I want you to interrupt me anytime on the slide we're talking about as close as you can so that we can discuss it. This is your show. This is the show. You need to learn what you came here to learn and make sure you direct me in the right direction because I'm willing to talk about anything you want to talk about. So we'll spend a good amount of time together. So let's get started. So let's see. I click on that so it'll pay attention to me. All right. So this is copyrighted. All these slides belong to ASHRAE. If you want to use them for something else, you have to ask their permission. The ASHRAE is a registered provider of any kind of PDHs that you need. This program will probably have them for you. It also is for the Green Building Council. It just about covers everything. The main thing about me you need to know is that I've been either a contractor, a consulting engineer for little buildings or big buildings. I've been energy services type contractor, and I have been involved. I have been on the ASHRAE committee since I heard it was going to be the code for the nation, and we were writing it in code language and put it out in 1999. And so I am very familiar with the requirements in the code, and I have been training on it since the 2004 version. So I am willing for it to be diverted from my slides any way you want to. I have my own company that has a patent that does kind of digital twinning type work. And then the main thing I do is I'm Federal Mechanical Practice Director for Jacobs, which is a large engineering firm, and I'm doing federal buildings mostly, and that's very interesting work for me. The course outline, we're going to go through the every section of the standard. We're going to do the only thing we're going to pull mechanical and surface water heating out of order of the other sections, just because it's an ASHRAE course, and normally people are interested in ASHRAE mechanical and stuff. I'm going to go ahead and turn my camera off. I just wanted you to know I was a live person, but since I use my arms a lot, I didn't want to be distracting down the corner. So I'll turn that off, and then so we'll just go through the whole section. So the learning objectives is we're going to describe the background, and we're going to let you know something about how the 90.1 standard. We're going to try to describe all the updated requirements from the previous versions in the technical sections. That's lighting, HVAC, building envelope, power, and other equipment. We'll describe the changes in the 2022 with context for understanding and applying those changes and why they were made. And we will apply the new paths for compliance, which is we will teach you how to look at that, apply it. It's a whole new section, and also section 11 is a whole new section. So we'll spend some time on those two sections. We do not in this course, because we don't talk much about Appendix G and how to build a model, because we're telling you the requirements and how the requirements changed. We'll spend a little time on Appendix G, but that's not the main focus, is how to run an energy model. This is more of the prescriptive and the things, the requirements that are in the standard. So here's the historical look at 90.1. It started in 1975 as a reaction to the oil embargo. And then it rolled pretty easily around until 1989 when it had a big drop in energy use, a big improvement. And at this time, the federal government between 1989 and 1999 adopted it as the code for commercial buildings in America. And in 1999, we did issue it in code enforceable language, which was the first ASHRAE standard to make that conversion. And then we rolled just normal. And then in 2004, we had a pretty good savings, and this became the DOE and ASHRAE agreed this was going to be our benchmark. Anything we did after that is going to tie back to the savings since 2004. So that became the benchmark that we work against. So 2007 was normal, but 2010, for the first time, ASHRAE and DOE agreed that we would issue a 90.1 standard that was 30% better than 2004. That was the first time we had a mandate. Normally we do our best and we do what we think is important. This said, we don't care what you do, but you're going to make it 30% better than the baseline 2004. We pretty much made it. We had one change that was challenged, and it did not get in the code until 2013. So we would have made it exactly, but we did not quite get there. Then in 2019, I'll switch from the other way, but these are the savings for the last 2016, 2019, and 2010. You'll see that I use these three because a lot of in our standard, I put a lot of the changes for these three because a lot of people have been working on the 2013 standard for a while. And so I think that these will be the changes that you might not be as familiar with. It was adopted by the Energy Conservation and Production Act of 1995. That's what happened when the federal government adopted it. And it's been amended several times since then. So now, let's zoom into what we're doing now. Here, starting with our 2004 goal listed as 1. That's our baseline. And now we're down to 2022. So 2022 is the first step in a 4-step issuance, 22, 25, 27, well, that should be 28, and 31. So we're going to step through there in 4 steps. We're going to get to net zero carbon. So we're going to drive it down by reducing the energy use until what's called the technical potential of the building. And at the same time, we're going to increase the amount of renewables we require until we're a net zero carbon building. And so in 2031 standard, we'll be a net zero building. In 2022, between 2019 and 22, there was 89 addenda, and 39 of those had direct energy impact, reduction of energy. But out of those 39, the model, the way we keep score is the national lab runs models for us. And those models are our official scorecard. And the DOE looks at those models when they're determining we're doing better than the 2019. But anyway, it's got to be modeled for us to get credit for it. So even though we know that 39 of them would have saved energy, only 21 of them could be modeled. And that's because either they impacted a system that is not included in the models at all, like a swimming pool, or the model wasn't capable of modeling that requirement. So we do that every time we lose a certain amount, and it's worse when you're going to net zero, when you're trying to get everything, but also it means, are our models showing the real world, or are our models not quite connected to the real world? And since most of the things you're going to be looking at have something to do with models, or many of the changes we're making have something to do with models. It's very important, and that's a good question of whether the problem with modeling versus some other form of proof. So this, this is this. I want to make sure you understood what the technical potential was, and it's based on research project 1651, which is an ASHRAE research paper. It was written in 2016 by Jason Glazer. Jason Glazer is a member of the 90.1 committee and has been for almost as long as I have. So what he did was he took the most advanced building energy changing methods available in 2016. No matter what they cost in 2016, and the assumption was that by 2030, which is when the paper was supposed to be telling how to hit that technical minimum by 2030, he said those would be available and in common use by then. And then he combined them to drive that building energy down to as low as you could possibly get it. And it used Energy Plus building models, the same building models that are being used to keep score for us. And then he made all those changes to it. The end paper is 640 pages long. It's one of the best technical papers I've ever read. And it goes through just like you would on a design and pick those possible, there were 400 different possibilities that he worked on. And he knocked it down to a handful that he used in all the models and all the climate zones and all the building types. And then he produced his paper and set for all those building types a max technical potential. And this is an example. This is a medium-sized office building in Chicago, which is climate zone 5A. It's 53,000 square feet. And based on the baseline building, typical building of that type in 2016, it had a energy use, thousands of BTUs per square foot per year of 37. Now, using all these changes, he was able to get that down to 12,000 BTUs per square foot per year. And that is the technical minimum. That's what we've adopted, is that technical minimum you can do on an office building. So, and he did this by these measures, and these measures are explained in the paper, but external lighting, office equipment, internal lighting, day lighting, etc. And you can see these are the loads and what they applied to, and those are explained at the bottom, color coded and by each thing. And you can see that as he did something on internal lighting, the internal lighting, it's internal lighting, light blue, that should get shorter, right? That's office equipment. This is lighting. So that shrunk that down just a little bit, but it shrunk it down. Anyway, so this is the heat got bigger. Anyway, this is the way that works, and you can see that it eliminated a lot of the bars when it got to the bottom. But it is a very good, straightforward way, and I use this now myself. When I'm looking at a project, I go back and open up that research paper, and I say, well, I should consider doing these things because they had the biggest impact on the savings. So that we're not exactly following this method exactly. This is what the Pacific Northwest National Lab suggested, that we go through the paper, but it didn't impress enough. Some of the people want to go their own direction and use their own savings. So I would like to be able to say to you that that's the path we're going to follow to get to net zero, but it's not quite, because like I say, it's a big committee, and there's a lot of people that that aren't following that path. So anytime you have a question about something like that, please interrupt or just make sure I know you've got a question so we can discuss it while we're talking about it. So as of June 2024, this is what the energy codes that have been adopted is related to our codes. Sometimes this will be an IACC code, but IACC code is tied tightly to 90.1, and so these are the equivalents. And you can see that there's some states that are on 2019, and some of these states obviously are at least as good as 2019, if not better, especially the West Coast. New York's has some new code. They've written some new codes. So that things are moving along a little bit better. The map looks a lot better than it used to look. But the states are supposed to, according to the law, they're supposed to adopt 90.1 or something better than that, or equal to 90.1 or better, 2 years after after it gets adopted by the DOE. So we issue the code. The DOE has about 2 years to do a study of it. They take the study and they give it to Congress. Congress makes a determination that yes, we should adopt. It will save energy and more energy than it costs, and we should adopt it. And then the states, the federal government has a year. The states have about 2 years to adopt the code. Now the problem is that the states, there's no penalty for not doing it. And sometimes they adopt it and sometimes they don't. So that's why the map looks this way. Now, if there's a reason that a big federal program moves into that state, a lot of times to get that money, they'll have to make the adoption. But there's no teeth in the law. So again, I've showed you this before when I said what we were going to do, just to make sure you know this is the organization of the standard. There is tied into these 13 chapters plus appendices, and that's what makes up the standard in order. These are the appendices. I will talk through them just because it's important for you to know what's back there. When it says normative, that means it's the same as being part of the standard. It had to go through the same review process, and it carries the same weight as part of the standard. When it says informative, it means it's for your use, but it is not. It didn't have to go through the same review, and it's not part of the standard. So normative Appendix A is how the envelope works. It's got all the information on the envelope, and it tells you if you have to have a U factor, a C factor, which is the same as a U factor except underground walls, or an F factor, which is a linear insulation along the edge of a floor or a slab. If you have to get those, you need to go to Appendix A to get those. These are the U value type. Anybody could give you the R value, but if you want to use the U value in your calculations, you need to get them from those tables that are in Appendix A. Informative Appendix B, still open. Informative Appendix C is the methodology for building envelopes trade-off. So if you're going to do the trade-off methodology for the envelope, there is a method, and it's a modeling method. You'll have to run a model, but it's under kind of strict requirements so that you will have to model some HVAC equipment to see that you're saving the savings based on what the envelope is, but that's a requirement for trade-off. Now, I'll say it again when we get to envelope, but just so we make it clear, the best way to do a trade-off on the envelope is to use ComCheck, because it is accepted to use ComCheck. It runs the equivalent of this model in the background to give you the answers, and it's much easier than you building a model. Appendix D is retained for future use. Informative Appendix E is informative references. So what that means is that if we give say SMACNA, or we say some name for something, AMCA or something in the standard, that gives you the reference. You can go back to E and you can see what that reference was and how you might get a copy or find out who does it and all that sort of thing. Now, informative Appendix F is what we do is the DOE, okay, officially, ASHRAE has the right to regulate the equipment used in commercial buildings. That's called, it's three-phase equipment. So it's got three-phase power. It's for commercial buildings. ASHRAE's been given the right to regulate that building. By regulate, I mean that we're going to set the minimum efficiency requirements for them. Now, the federal government or the DOE sets the requirements for single-phase equipment, residential equipment. They do that. All right. Now, sometimes some of the equipment that are used in office buildings and buildings of all kinds that we regulate, they do something, they make some requirements for. And when they do that, we don't want you to have to go look for them, so we put them in the standard. We put them in under Appendix F. So they have requirements and things, so we want to make sure you get in one place where they do that. Normative Appendix G, that's the performance rating method. That's the model you have to run almost anytime you have to show that your energy efficiency is as good to meet the requirements or better than, mostly better than the requirements from 9.1. Or Index H is additional guidance for verification, testing, commissioning. So we've tried to get a lot of information. Commissioning is important, but because of the nature of commissioning and the agreement, we're consensus standards. So everyone has to agree on things that go into the standard. And the main problem that comes up under commissioning is if you put it in a code, then you have to say what happens if you don't make it. So that's the big question. So you're at the end of a project, you've spent millions of dollars, you're getting commissioned. We put a rule in about commissioning, and you fail. Well, what happens? Tear the building down or what? So we get a lot of arguments and a lot of stuff about commissioning. So we ended up with having some commissioning in the standard, and then this informative appendix that gives you a lot of guidance on commissioning. So informative index I is using other metrics in conjunction with appendix G, performance rating method, when approved by rating authority. What that is if you were a code official, or you are a code official, and your jurisdiction wants to, instead of using cash money, which is what the 9.1 is, it's on dollar savings. If you would rather use carbon or some other metric than cash, there's the math that you would have to do is included in Appendix I. So it tells you how to convert to a different metric. Informative Appendix J is a set of performance curves for chillers. So if we're going to run models to prove everything more and more and more and more, and you can't get a performance curve from the manufacturer because those are secret, and they say, if we showed you the curve, that our competitors could figure out what we're doing differently than them, and it's just not something we can do. So we made up a set of performance curves with a lot of guidance from manufacturers, and we want you to use those for your baseline buildings. So this means that everybody will be using the same curves, and so all the designers will have an even playing field. Plus, these curves should be beneficial because they are actual curves for good chillers. Now, you can, if you don't have one for your and want to use it for your for the building you're proposed to build, then you can use them there too. But they're designed for your baseline building so that everybody has the same curve they're working from. It's fairly standardized. Informative Appendix K are some figures. We'll talk a little bit about thermal bridging over the next 2 days, which is new requirements of the standard. Informative Appendix L is mechanical systems performance rating method, and that backs up a new path to go through the prescriptive section of 90.1. So this will be a whole new section, and this will be a whole new appendix to support that section. Informative Appendix M is addendum descriptions, and that is every, I think it was 89 addendums that we have in this. Every one of those will be listed in Appendix M. It'll tell you what section they did make a change to. It'll give a brief description of what that change was. Then Annex 1 is of something we do for you also. It's got the reference standard for ASHRAE weather. 169 is the weather group, and they sell a standard 169, and that's the weather. We have pulled out what you need to use to work with 90.1, and we're giving you that. We got permission. It was kind of a big deal even from our own organization that we got permission to give you that for free. So you will have that available to you. So I forgot to. What we're going to do is in an hour and a half from when we started, we're going to have probably I'm going to give you maybe let's say 10-minute. You can raise your hand and say we need 15 minutes, and I'd probably let you have it. But let's say 10 minutes just to break. We just have one break in an hour and a half, and if you need more than 10 minutes, let me know and we can work that out. But I wanted to make sure that I had done that. Set a timer, and so sorry, I'm distracted for a second. All right, so the standard keeps growing. So right now it's 164 pages long. So you deserve more money to design a job than you got when you're working off a different standard. In 2019, it was 422 pages. In 2016, it was only 380 pages long. And before that, we had 2 columns on every page. So it was a whole different look to it. It's much easier to use with 1 column on a page, but it was only 221 pages. So at least it was a thinner book. So 90.1 technical subcommittees. We have section 5 is the envelope subcommittee. Section 6 is the mechanical subcommittee, and we handle sections 6 and 7. That's the subcommittee I'm a member of. Section 9 is lighting, and those are also the chapter names. When I say section, that's the chapter. It's being written and controlled by the lighting group. Now, the lighting group is called Lighting and Power, and they do 9 and chapter 8, which is also called the Power chapter. I need to fix that up because that's kind of a change that we changed their name a little bit. 12 is Energy Cost Budget and Appendix G. So that's a subcommittee. We have a Format and Compliance subcommittee, and they help make sure that our words make sense and that we're using the same kind of terminology throughout the standard, and also how the compliance chapter, which is chapter 4, is written. Any technical subcommittee can add to chapters 8 and 10, which 8 is power and 10 is other equipment. But now 8 really belongs to the lighting and power subcommittee. Title, our first 2 sections, 1 and 2, is title is 1, purpose and scope is section 2. So the purpose of the standard is to establish the minimum energy efficiency requirements of buildings other than low-rise residential buildings, and for 2022, it's new, sites for design, construction, plan for operation and maintenance, and utilization of on-site renewable energy sources. So notice that we have a plan for operation and maintenance. We know that it's very important that we build a very efficient building, and then within a few years, it is not as efficient as it was. It starts to use more power. So we need to be able to control operation and maintenance, but it's very difficult for a building code that is enforced as you occupy the building, and nobody else is going to come and enforce something we put in an operation and maintenance. We're having trouble coming up with good things to control. So we try to work on closeout documents and make sure that we're getting closeout documents and guidance, because one of the things we've identified is when the operators change, that they bring the building operation from their old building, and if we have a different sequence of operation for our plant or for the way we operate, then it gets messed up. And it's very important for the training to be able to be repeatable for any employee changes and things like that. So we're trying our best to add things. And then finally, utilization of on-site renewable energy resources. And as I said, this year, 2022, or this edition, 2022, is the first time that we've actually required any on-site renewables. We'll go through that in some detail. All right, 90.1 2022, you might not notice it all, but we actually changed the name of the standard. We added those sites. So energy standard for sites and buildings except low-rise residential buildings. So sites have been added to the name of the standard. Scope. This standard provides a minimum energy efficiency requirements for the design and construction and a plan for operation and maintenance for new buildings and their systems, the portions of buildings and their systems, new systems and equipment specifically identified in the standard that part of the site, new system equipment of existing buildings and new equipment specifically identified in the standard that are part of a process application. Now, there's a couple of things, I read them out loud, and I don't normally try to read a slide to you because I know you can read, but there's a couple of things in here to take note of. First thing is this is the minimum efficiency requirements. And I've already told you that in 2031, the minimum efficiency requirements for any building built in America will be net zero carbon. This is nothing we ever anticipated. I never anticipated that we would set a minimum standard of zero. Now, we had some, stretch codes and some different things that I thought might go there, but we are 90.1 has been mandated to get there by 2031. And so that to me was a surprise. Second thing is new systems and equipment specifically identified standards that are part of the site. You see that wording is exactly the same as the fifth thing, which is new equipment or building systems specifically identified that are part of a process application. So what happened was back in 2010, when we had that mandate that we had to save 30% better, we went after data centers because data centers were in the newspaper all the time, or in the news all the time, saying that they used more power than anything. They were using power like crazy. And so if we could regulate them and reduce that power, that would be a lot of power we were reducing, and we could maybe make our 30% goal. So we went after data centers and we added them. Now this was the first time we went after a process. So that's number 5. So we changed our standard then to say new equipment or building systems specifically identified in the standards that are part of a process application. So we were able to get them because we specifically identified data centers as something we were going to regulate. That's the way we went through it. Now, we talked to all the people that you know and I know that have to do with data centers, all the people that do mechanical equipment for them. We did all the people that design them. We brought everybody in and we wrote rules for data centers. What we did not do was we didn't call Microsoft and Google and all the people that own data centers. We didn't call them and say, hey, we're about ready to regulate you. They were not happy. So they got permission from ASHRAE to help write 90.4, which is the energy code for data centers. And it did not stay as part of 90.1. It stayed for a couple of cycles, and then it rolled over when 90.4 was adopted to 90.4. We reference people over to 90.4. They reference people back for a lot of things in their code to us, but it is a separate code. And the main reason is because we did not do a good job of talking to the owner of the building. We just talked to everybody else. Now, we've done the same kind of thing with this site thing. We're not going to, suppose you own a steel mill and you have all this stuff on the site. Well, what we've done is we promised not to sneak up on you and say, all right, all that stuff that's outside your building on your site, now it's regulated to meet the 90.1 standard and you got to fix it. Because we'll have to talk to the steel mills first and say, we want to write some rules for this equipment that you have in your yard. And that's the idea. So we've learned our lesson. Criteria for determining compliance with these requirements. I'm continuing on the rules and provisions for this standard does not apply to single family houses and related incidentals. It's easy for you to say, structures, multifamily structures of 3 stories or fewer above grade. So that's a key, that if it's shorter than 3 stories, then and a residence, then we don't have anything to do with it. Apartment buildings, things like that. Manufactured houses and modular and mobile, or buildings that use neither electricity or fossil fuel. Now, this and related incidental structures was added as part of the idea of sites, because we had days of discussion about, suppose a guy opens a shop, a car repair shop in his garage. Are we going to say now it's regulated as a commercial building, or what are we going to do? So we tried to work around that by calling them related incidental structures. But if he builds a barn by himself with 4 or 5 bays, then we would probably try to get it up. But it's up to the authority having jurisdiction how they apply things like that. Where specifically noted in the standards, certain other buildings or elements of buildings or sites shall be exempt, and this standard shall be not used to circumvent any safety, health, or environmental requirement. So if we ever have something in there that authority having jurisdiction, or if somebody says, no, that's not safe, and our requirements for safety require something different, then safety always rules. Okay, section 3 is definitions, abbreviations, and acronyms. I'm not going to talk about it because I can't just sit here and read you the definitions, but it's very important for you to look at that section, because it may not be, our definition of it may not be the same as yours. Anything in the book that you see in italics means it's got a definition back in the definition. So it's worth looking up. If you see anything in the standard written in italics, it might be worth looking at just to make sure you're thinking the same thing we are. Also, there are certain things such as in daylighting that, there was a lot of information about daylighting and it would make our book, the technical section on envelope too thick. And so we put a lot of that information into the definition of daylighting. And so you would need to look at that for some things. It may be the only place to get some information. Section 4 is administration and enforcement. Enforcement's very important. The compliance paths, what I'm trying to show here is that section 4, there'll be 6, 4, 8, or 5, 4, 2. You know, but the second number being a 4 means it's mandatory. So there's very rarely a chance for you to not have to do something with a second digit that's a 4. So you would have to do it. Now you have to do all the mandatory. Then you can use Appendix G after you've done the mandatory. That's a model. So you can run a model, and as long as the model uses less energy than the baseline building, then and you've met all the requirements that have a 4, the mandatory requirements, you can use it. Same thing with ECB. Now the ECB was written a long time ago, and it was written just for complying. The rules in it are tight. It's not for doing better than, it's just for complying. And we have not done away with it because it is in a certain way easier to show compliance, and it is a well-balanced way to do it as far as, you can't, it doesn't allow you to overdo one thing and then put a bad something else in. So it's a good way. Now, starting in 2016, we started allowing Appendix G to be used as both. Before, it could only be shown better than, it could not be used for compliance. But starting in 2016, when we made some other changes, we allow you to use it for compliance and to show better than. And then the other way is our prescriptive section, which is more or less what we're talking about today, and that we're going to show you all the prescriptive requirements. So you would use the prescriptive, you would use the mandatory, then the prescriptive, and then the added energy requirements that we'll talk about. New section that has to be used now. So you can, after compliance, you can pick a few more things to do to meet compliance. So Appendix G 2222 performance rating method. All right, so this is the same as it was in 2016. And so we'll go through it in case you haven't used it, but it's a new method that started in 2016. And the main thing about it is that proposed design is based on 2022, just like normally, but the baseline building is always tied to our baseline 2004. So this building is built to the requirements of 2004, and it's used to compare to the building built today to the 2022 requirements. So the performance rating method, what way that works is you'll calculate an index of merit, is what we'll call it, and basically you'll calculate. Well, I'll show you. It's harder. The words are harder to understand than look at a little bit. So when you're using Appendix G, the performance cost index, PCI, shall be less than or equal to the performance cost index target, PCI sub T, when calculated among the following. Now, this is how you use those two to show savings. It's not, we'll show you the calculation on the second page, but it's pretty straightforward. Your actual savings will be your target minus your actual divided by your target. Just that's pretty common. But in the calculation, let me run down here real quick. So this is the actual calculation of your target. So this has the BBUCE, which is the base building unregulated energy costs. That's plug load, et cetera. Things that we don't write, we can't, we don't, we haven't written any 90.1 requirements for. The other thing is the regulated. The base building regulated energy costs are the things we have written requirements for. So here's the base building unregulated, and you'll see that it's out here by itself, because the idea is that since we didn't make any changes to it, whether it was done in 2004 or 2022, this number will stay the same or relatively the same. And you can change it if you say, well, I'm going to use some kind of energy star equipment or something that's not in the standard at this time. And you can do that. It's just that we, in the calculation, have decided it'll be close enough to equal that we'll just adopt it. Now, this is the regulated. So this is things we have made changes to. And there is a building performance factor in a table that will take the 2004 regulated, because you're going to do that. The baseline is based on the 2004 requirements. You'll calculate that, and then you'll multiply it by this factor, and this factor will convert it to a 2022 number. And then this is a complication. This is minus the, you've got to take the regulated load minus what we did with renewables. So this is your renewable factor, and then we'll divide it through by the total energy used in the baseline building. And so that's the way we'll go about it. Now, to limit the use of renewables when using Appendix G to show compliance. So the rules are that that to show compliance. Now, if you're going to say I'm 30% better than the baseline building, you can put as many renewables as you want to. But if you're going to say my building complies with the standard, you cannot use more than 5% of your building energy as renewables. So if you reduce your building use by renewables, then instead of putting a good wall on or a good insulation on the roof or something, we're not going to let you do that. So we'll only accept 5% of your renewables max. And that's what PRE is used for. Now, the factors are discounts. So you'll run the baseline load, and then you'll multiply it by these numbers. And that is what we believe is a difference in 2004 and 2022 regulated parts of the building. So we've reduced energy use in what we regulate in climate zone 3B by 54% in an office building. That's the way you read that table. So you can see that from 2004 till now, we have some pretty decent reductions in the amount of energy we use against the regulated portion of the load. So just to have it, since you'll have these slides, and that's the 2019 version. Sometimes it's good to kind of look at it. Suppose that same office in 3C is 0.48 in 22, and in 3C it hadn't changed at all, it was 0.48. And you'll actually find some of these factors that in 2019 indicate we save more energy than you are saving in 2022. And that's just the way, like it showed you before, the models run and models change based on different stuff. So if we had that little office building we've been looking at, climate zone 5A in Chicago, 50,000 square foot, suppose we ran the proposed building performance and said a 2004 building would use $90,000 a year in energy. And your baseline building performance is 2000 and why does it say that the performance has been calculated $90,000 a year? Baseline performance is 2010 a year. Oh, proposed building performance. Sorry, I read that wrong. The proposed building performance is 90,000, makes perfect sense. The baseline building, the 2004 building, is 210,000. Your baseline building regulated energy costs, so 167,000 out of the 210 was regulated. Your baseline unregulated was the 43 that makes up the difference between 167 and 210, and your renewables that you're going to take out of it are the shown there. I guess it's $80,000. Yeah, calculates out as $80,000 at 5% of the wattage, and then 80,000 minus the $90,000 a year that we have in a proposed building divided by 210 is 0.472%, so it's less than 5. So you can discount it by 0.04762. So that's for the renewables. That's an adjustment you make for the renewables. So then you look at the table and you pull out that 0.49 for that climate zone 5 building, and you multiply that. Calculation is cost index equals proposed building divided by baseline building, which is the 90 divided by the 210, which is 0.43. And then you calculate your target, which includes that 0.49 as your baseline factor, and you come up with 0.55. And since 0.43, which is your actual, is less than 0.55, which is your target, then the building complies. And you can go back and plug it into that first equation on that first slide, and you can see that you've actually saved 22% more than a building that just complies. And that's the way it works using this new way to use Appendix G since 2016. So the other thing that's in the compliance part of the section 424 is inspections. And there's a nice list of inspections that are required to be done by the code official on fenestration, on opaque assemblies, which means things you cannot see through, continuous air barrier inspections, operable fenestration door inspections, loading dock, weather seals inspections, and other inspections required. Major expansion of the requirements for verification, testing, commissioning of building systems and controls, and the building envelope in the starting in 2019 and continuing in 2022. Building system verification and testing requirements. These, again, there's a long list of them, and those are required to be done as part of the code. So we're trying our best to make sure that someone checks the work as part of the energy side of a building being occupied. And then commissioning, finally. We do require some commissioning on the envelope and on the heating and ventilating, power, lighting, other equipment, and and also we do require when things are modeled. All right, so this is the weather data that I talked about earlier. This has been since 2016. We did change the climate zones. We added climate zone 0, which is extremely hot and humid, or 0, which is B, which is extremely hot and dry. As you can see at the top of the America, the moist side of the United States, where the humidity is a problem, is to the right side. And then the dry side, which are the deserts, are in the middle. Those are Bs, As and Bs. And then C is California, which we call a marine climate, which is its own climate. So these are our climate zones. And you can see that there's an AO and a OB and an OA now. And those are, again, the extreme weather, and there is none in America. Do apply to places like Saudi Arabia and some places like that, Vietnam, certain cities and towns. So here's a world map, and you can see that some places on the world map are extremely hot and humid or extremely hot and dry. So again, those are not used in America. So talking about weather, something I do is something called Climate Consultant, and that is available for free on the web. It was actually developed at UCLA, but it's obtainable from other people now, and UCLA doesn't seem to be the head main one supporting it. But anyway, so it's a good idea to look at the places you're going to, and I like to look at the site chart that they do. So every one of these little dots is 1 hour of weather data. and it's plotted on a year's worth of weather data. It's plotted on a site chart, and then they offer 16 uh, energy saving measures that you can turn on and see what the impact is by turning, I've turned on them all, so all the dots are green. If I have some red dots on there, that means that those are not meeting the temperature requirements that I've set for the building. So it is a nice way to get an idea. Now, this is Honolulu, and the reason I put it on there is because 2016, we chose climate zone to represent climate zone 1. We chose Honolulu, and it does meet the requirements to be a climate zone 1 place, but it is so tightly structured where most of the problem is in humidity, and it just, it's a little bit hotter than it should be for almost every day. And so it meets the requirement because it's hot enough degree days, but it's really not that hot and it's probably not that cold. So it was not a good selection by us. And so in 2022, we moved back to Miami, and that's a much better selection. So let me explain a little bit how climate zones work. Is that the cooling degree days here along the bottom. So that's 1,000 cooling degree days, that's 7,000 cooling degree days. And heating degree days are up here along the right-hand side. And these are, well, I'm sorry, the top of it's in Fahrenheit, the right-hand side's in Fahrenheit, the bottom's in Celsius, and the left's in Celsius. So you can use either one you want. But anyway, the heating degree days are in the vertical. So if you're in climate zone 0, you have all cooling degree days and very few heating degree days, less than 3,600. And then if you're in climate zone 1, you have a little bit more, a bit less cooling degree days, and 2 has a little bit less. But we stayed constant on the heating degree days. So then once you get to 3, we're still not adding heating degree days, but our cooling degree days are getting pretty low. So it's a good neutral place. A lot of you could think about that as being a good place for your economizers, et cetera. So then it starts to go up for the number of heating degree days. So you can see it's climbing up on heating degree days where it's not moving at all, or we're holding it tight for your cooling degree days. Now, then we take a slight step back that we're to 2,500. So we got less cooling degree days, and the rest of it is adding heating degree days as we go up to climate zone 8, which is way up in Alaska, and 7, which is a little bit in Alaska, and 6, which was down here in Texas, people working outside on loading up, working anyway. So these people in climate zone 8, it's very cold. That's all I'll say. And that's the way this works. So it's good to recognize it, because if you'll notice, it's all on heating degree days, and it's also, this hot and cold climates are also on rainfall, precipitation. It doesn't ever mention humidity, which is very important as a mechanical to think about, that there's not anything in the standard when we talk about climate zones that talks about humidity. Now you may think, well, it rains a lot, so you've got a lot of humidity, but that's not necessarily true. Also, in places where it snows a lot, and they're considered to be moist or A environments, they sometimes complain that it's not the same as being in a hot, humid spot, even though they get a lot of snow. But you can see that the way we calculate October through March and April through September. So, like Montreal works for sure, because I had to test it one time when they were complaining. So they do get enough precipitation in April through September to qualify. All right, climate zones for Texas counties. Now this is interesting because I told you that in 2016 it changed. We added the zeros, and we adjusted the temperature that the 169 had run the equations for found that in gathering the data that it was actually getting warmer. And so all the climate zones kind of snuck up. And so climate in Texas, we have 3 new counties down here in the Panhandle that are climate zone 1. We've never had a climate zone 1 climate in Texas previously, and now we have 3, and climate zone 2 moved up to the north and took over such counties as Dallas and Tarrant, which is Dallas and Fort Worth, which is millions and millions of people. So it was a big impact, and it's an impact at each state. We always, we go by counties at each state. It got a little warmer, and the climate zone did sneak up a little bit. Now we're going to go into real technical sections. We'll start with the HVAC and mechanical, section 6. This is the prescriptive. Well, this will be both prescriptive and mandatory. So compliance with section 6. This is even a little complicated for me. I have to think hard when I step through it, but it does explain it well if you get through it. So section 6, it starts off with section 6.1, section 6.2, which is the boilerplate type stuff that compliance and requirements, that we've just talked about. Now 6.2.2 is a simple path. The ASHRAE, ASHRAE mechanical is the only, well, there's 2 of us now that have simple paths. We've had it for a long time. Now, the simple path is the only thing I'll tell you about that does not have to go to the mandatory, because all the mandatory things that apply to simple path have been included in the simple path. So they're there, you just don't have to go through 6.4 to get to them. Now, that goes off and you go the simple path. So you go from 6.2.2, which is the compliance thing, through the simple path, 6.3, and then everybody still has to go through 6.7, which is submittal, 6.8, which is equipment efficiency, and 6.9, which is that commissioning and testing I talked about. But that's the easiest thing to do. We'll have a slide on it a little bit later. Now, the rest of everyone that didn't do the simple path has to go through mandatory now. So you'll do the mandatory requirements, and then you'll go to the prescriptive path. So 6.2.2 will send you the prescriptive path, and that'll be 6.5. In 6.5, you'll do all the prescriptive requirements, and then you'll come back up and have to do those submittals and everything. Now, if you don't want to do the prescriptive path, you can go new this year. You can, if you have a data center, you can go to over the 90.4, or you can go to what's called the TSPR, which is a compliance path, a new compliance path instead of using the prescriptive methods in 6, and that'll be, you'll do that, and then you'll either go computer rooms or you could, if you you don't have to go through, you don't have to go through the prescriptive requirements if you're going through either one of these. All right, then you go back up and through the 6.7, 6.8, and 6.9, and then so this is RTS. Let's say I screwed myself up again. So this is going through our system 6.5. So this, I'm going to the computer rooms or I'm going to prescriptive, and so you do have to go through the prescriptive requirements, or you have to go through the computer requirements and then go back up. Now you come down here finally, and this is the performance path, the TSPR, and using Appendix J, and you do not have to go through 6.5 at all. So you go this way and back up and out. All right. So again, this flow was written by the Pacific Northwest National Labs. It makes sense. It works. You just really have to be thinking when you go through it. All right, so simplified approach. We did that back in 1999, and we said that it would be something that most of the buildings in the country, 80% of the building permits are for buildings that fall in a simplified building, and it's buildings of 1 or 2 stories, less than 25,000 square feet, single zone systems, air cooled or evaporative cooled condensers. And we're going to just put those in, make it simple, and it'll be one page with a cover page, and we're through. Now, but we made a mistake in that the requirements for the simplified approach are consistent with prescriptive requirements. So what has happened is now there are 21 21 requirements for a simple building, because every time we passed a prescriptive change, we had to check if it would be required in the simplified building and add it to the simplified buildings. And so they're not simple anymore. There's too much in there. So we've offered twice to get rid of it. The full committee says no. Everybody loves the idea of having a simple approach. You have to keep it. So we do keep it, but it's not so simple. Now, what we do when we're working on making changes to the standard is we use an integrated design. So our full committee, remember, has all those envelope, lighting, mechanical. We have everybody in the room and we're working on the changes. So we think that's the way you are to approach projects too. So first off, we look at plug load, the lighting people do, the lighting. They're working to reduce that as small as they can make it. And the envelope people are working as hard as they can to reduce the amount of energy, of heat that is transferred through the building. And outside air is controlled by ASHRAE 62, and they don't care about energy at all. They keep requiring more outside air and stuff. But outside air is now in a normal building without big process loads. It is probably the biggest load that we have for HVAC. It's based on people, and people also are a heating load themselves. So we get all those done, we reduce those as far as we can, and then we approach the HVAC equipment, because the smaller the equipment, the less energy it uses always. And we minimize the load, and then we start to decide what the most efficient approach and the most efficient equipment to serving that load is. We also, in the standard, have exterior lighting, parking garage, and service water heating, which do not add to the load of the building, but are important things we regulate. Now, one of the big things, like I told you, is ASHRAE has been granted permission to control the efficiency of equipment. So far we have 21 pieces, or I say we have 21, it's about right. We have tables set up 681 to 6821, and each one of those tables are a different piece of equipment in general. We regulate those, and when we say, we have that term up there that says unregulated. We don't like that unregulated because we never reduce it. And if you're trying to show a building does better than, it's better to have, at the end you divide through by the total amount of energy used in the building. If that's a big number, then your savings are going to be smaller. If that's a smaller number, then your savings will be larger. So if we can reduce the amount of energy in the unregulated department, and regulate and reduce it, we're much better off. So we keep trying to add these tables and add more equipment to what we do control or regulate. So when one or more requirements are listed in those tables, you've got to require for meet all the requirements. In 2022, we modified the air source heat pump requirements and added the new metric, a new COP metric, and we also added ceiling fans. If the equipment is not listed or is operated outside the listed range, it can be used without requirements. That makes it unregulated. That makes it fall in that other table that we're trying to run away with. And then we mentioned to you that we have new normative Appendix J, which are those chiller curves, and they're required for use in the baseline building, can be used in the proposed building, but it's a major improvement, we think, in standardizing and optimizing the models. So here's an example of what you'll see, that curve, and you'll have to, if you've never looked at entering a curve into a load program, this probably won't make much sense to you, but this is exactly, if you opened up the load program you're using and to the part where they're using their chiller curves, then this tells you exactly what to stick into those programs. So in the standard, chillers are rated on two paths. One, path A is a chiller that normally does not run at full power, that is normally running less than fully loaded. And set path B is a chiller that runs mostly at full power. And so we have two possibilities. This one forces you to be more efficient. I think I'll have a slide on it later, so we'll go into it then. But anyway, there's two columns. So, and then these are the size categories, and these are the chiller types. Now, the curves are all these, here's air water condenser type, and then these are these, see, and these variables will be what your computer is going to ask you for to to enter so that it can build your curve and run it. So, and this gives you all the points. Now you'll look down here. So this references an output variable A. If the energy output ratio modifier is a function of temperature, is the capacity modifier to use. Energy ratio is part of the deal. Then you get all these coefficients, you plug them in, and then you run the computer program. This is one sample from the table in the book, coefficients for an air-cooled chiller, and gives you an idea. Like I say, you don't ever have to run this calculation. You just have to enter them in your computer. Then we changed window units. In 2019, there's a new thing called the Combined Energy Efficient Ratio, CER. It's a ratio of the total cooling in 1 year divided by the total energy from active, standby, and off modes. So it captures, before it was probably just all active, and now we're capturing if it's just sitting there waiting for you to turn it on. And so this is the CER, and it's a new table with the requirements. Variable refrigerant flow is, always kind of a interesting thing to regulate because, the way it works is it works much better if you have, is shown here, some in cooling and some in heating. And the way the inside works, where those hot refrigerant and the cold refrigerant, or those two heat rejection modes work with each other and save energy. Well, then how do you decide how often you're going to have two heating and two cooling to regulate? So we have not really given a very fair shake, tell the truth, because we regulate them pretty close to what we would regulate just split systems with. And so there was some study, and we did some adjustment in the values based on some new studies done. And so they're getting a little bit better, but I'm not sure. If I was you, I would not use our standard in modeling them as far as your energy model. I think they probably would never win because of their high cost. Mandatory provisions, controls. So in the mandatory section, after we regulate equipment, we put most of our controls under the mandatory. So we have zone thermostatic controls, dead bands, set overlap restriction, off hour, automatic shutdown, setback controls, optimal start controls, zone isolation. These have been around for ever. Now, the thermostat controls I always like to mention because it, does it make sense that we're making a deal out of it? Well, the supply of heating and cooling energy to each zone shall be individually controlled by thermostatic controls responding to the temperature within that zone. For the purpose of this section, a dwelling unit shall be permitted to be one single zone. So that means if you've got a little apartment with a bedroom and a front dining room and then a hall, you can put that can be considered one zone, not that the dining room separate from dining room den. Anyway, you can see that one thermostat per apartment. Now, the problem is that a zone is a space or group of spaces within a building with heating and temperature requirements that are sufficiently similar so that the desired conditions, normally temperature with a thermostat, can be maintained throughout using a single sensor. So if this VAV box has a thermostat, then that room's probably in good shape. But this, maybe the one up here, maybe the one down there, if this thermostat's not in the right place, and this area is not an area that's running at the same with the same occupancy type and that sort of thing, then people put that thermostat in the wrong place, or they try to put too many areas on the same box, and then it's not sufficiently similar so that the desired conditions can be maintained. That's when you get hot calls and cold calls, that sort of thing. So we also have off-hour controls, and that means that when the place is not occupied, then we normally turn off the system and then allow it to come back on after it certain temperature requirement. Now, we have some exceptions for hotel and motels, guest rooms. We are trying to reduce the energy used in these places, but they are in special places that people come in and out of, and also have some humidity requirements. So exceptions when they're intended to operate continuously, and HVAC systems not serving residential spaces and having design heating capacity and cooling capacity less than 7,000 BTUs. That is the change for 2022. In 2019, that number was 15,000. So we've cut that in half for these. We've really increased the amount that do not qualify for the exemption. New for 2016, modified in 2019. We did quite a bit of work on hotel guest rooms, and we changed again the modified in 2019. Set point controls occupied for 20 minutes, reset 4 degrees up and down, unoccupied and unrented. We adjust and 16 hours or 20 minutes with network control. So that red part was added in 2020. We added 62 requirements to prevent maximum humidity levels in 2022. So a lot of work been done over the time, but a focused area that not everyone's interested in for the hotel motel guest rooms. So the HVAC mandatory section for ventilation controls. Now, in 2022, we added, we've always had trouble with stair and stair vents. Motorized dampers are required to shut off except during life safety event or required by fire and smoke protection systems. Different jurisdictions have different requirements for these kind of systems. We added by thermostatic control systems this time. In the past, it's been a little iffy whether you could use, anything like a thermostat to control something for life safety. Now it seems that the way that they've rewritten the life safety side of the standard, it is allowable, and we took advantage of that. We want to close the building up as tight as we can close it. So we want to close every damper we can close as much as we can close it. Outdoor air intakes, vents, etc., must have motorized dampers. damper leakage per the table, you'll see in a minute. Ventilation fan controls for fans larger than 0.75 horsepower to shut off fans when not required. Enclosed parking garage ventilation. So we regulate parking garage ventilation because the building code says that you have to put in fans with a certain amount of CFM per automobile, et cetera. And that's a big number, and it uses a lot of energy. And so that might be needed when all the cars are coming in the morning or all the cars are leaving in the evening. But a long part of the day, you don't need those fans because nobody's running their car around in there. Now, or very few people. So we provide a system to automatically detect contaminant levels, whether it be for or for gas vehicles, and adjust the fan speed accordingly for each parking garage section. Must be able to reduce fan speed to 20% or less of the design capacity and all the fans must have variable speed drives. Exceptions are shown down when you get your slides or if you have them in the notes, but there are some exceptions. So we're going to use a sniffer to decide when we should speed that fan up or slow it down, and we can save some energy that way. Humidification and dehumidification control. Now, one of the things that we really regulate against is simultaneous heating and cooling, or heating and cooling the same air streams or water, back and forth, because that loses energy, obviously. So, but I live in Texas. I live in a hot, humid place, and there's hot, humid places. So we have a balance. Have to try to strike a balance. So humidistatic control shall not use mechanical cooling to reduce the humidity below the lower of a dew point of 55. Now, that's the normal dew point for supply air. Most supply air systems, or many standard design would be to supply air at 55 degrees. So your dew point comes naturally there. Or relative humidity of 60% in the coldest zone served by system. All that means is if you're going to dehumidify and you're just going to dehumidify, there's no other reasons to do it. They don't want, or we don't want you to reduce the air temperature lower than 55 to just do that. Now, you could have some other reason to knock it down to 53, but just to knock it down to remove humidity is something that, without the exceptions, we don't allow you to do. Some exceptions. Humidification. Humidistat control shall not use fossil fuel or electricity to produce relative humidity above 30% in the warmest zone served by the system. So this is saying fossil fuel or electricity, and it's leading you to use a adiabatic type system. So it'll be that spray type or something that does not use fossil fuel electricity if you need more than 30%. Control interlock where a zone is served by a system or systems with both humidification and dehumidification capability. Then you have to interlock them so that they won't, they don't fight each other and be adding humidity at the same time you're there are some exceptions, of course, for museums and libraries and certain places, and there are some ways to set it up to get around it. But usually you don't have to get around it unless you are in some sort of process or some special place. Dew point, when things sweat. You always have to think about, we mentioned dew point there, and on top that's pleasant, but as you start raising that dew point, you get more and more uncomfortable. So as soon as you start getting above 60, then you are in trouble, or start to get in trouble. And when you get 66 to 70, you are very in trouble, and then oppressive and miserable. Now, these are dew points. We like dew points because dew point is a straight line across the psych chart, and it isn't affected by the temperature of the air as far as the dry bulb temperature, which relative humidity, of course, it changes. There's a curved line on the site chart. So it's much easier to or to try to control a dew point than a relative humidity, because it just the relative humidity is affected, moves around on the chart, and it may not be uncomfortable. It's easy to say this is. Now, we require demand control ventilation in certain circumstances. So ventilation controls for high occupancy areas. Demand control ventilation is required for spaces larger than the floor area shown in table 6438. And here, this table is a new thing for 2022. So we'll explain the ventilation control a little bit. Demand control ventilation is a ventilation system capability that provides for the automatic reduction of outdoor air below design rates when actual occupancy of spaces served by the system is less than design occupancy. Now, this is very important, and you have to believe me, because I have people argue with me sometimes. I promise that we would, as the energy people, we would never say we're going to have demand control ventilation so that you know when to increase the amount of air into the space. When you design to ASHRAE 62 and you put the amount of air you're supposed to put in by ASHRAE 62, you as an engineer are never required to add more than that to meet your safe building. If you decide to, that's your business, but you don't have to do that. And what we're trying to do is to give you a signal that says, according to ASHRAE 62, this building's safe. The demand control ventilation works off of measuring the CO2 released by a person, and that is well documented how much CO2 a person releases at certain stress levels or certain deals. And that's the same way ASHRAE 62 set their requirements. And so we say you never have to go above them. Now, I have people say, oh, if that alarm goes off that you're above the ventilation, I have to start opening the outside air damper. Well, that's not true. You don't have to. You alarm to the owner, you alarm to the operator. They make a decision on what to do. But to automatically open it would cost you energy and might not be necessary. So that was our alarm for our part-time. I haven't heard. Let me see if I can find that chat box. Oh, we do have a couple. So we'll do that. We'll do that in a minute. Answer your question. We come back. Nobody said they want 15 minutes, so we'll take a 10-minute break, and we'll be there back at 40 minutes after the hour. Thank you very much. I'm back. Hopefully you're back too. So we have a couple of questions we're going to go over first. So what is the difference between path A and path B? Let's say for chillers. Well, chillers is the only thing we have two paths for, path A and path B. So the history of that is that we had the manufacturers, and it was when we started to put VFDs on chillers. Now, VFDs were expensive. So the manufacturers said that brought into us studies that showed that their chillers, if you were running at part load, would work better with a VFD and use less energy, but they couldn't afford to give us VFDs on chillers that met all our requirements they wanted a discount, in other words. They wanted it to be able to be less at full load, less efficient at full load, if they were more efficient at part load. So we said, well, shoot, just give us the one that is got all the copper and everything in it to be a good full load chiller, and then give us the VFD on it too, and we'll have the best. And they said, but nobody will buy it because it's going to be so expensive. So it took a while. We've negotiated quite a bit, but we decided to divide chillers into two columns. A chiller that's going to run mostly at part load, which will include a VFD more than likely, or something to vary, something equivalent to a VFD. And that meets one bit of requirements. And then if you're saying my chiller is going to run mostly at full load, then you'll look, if you look at the table, you'll see that the full load requirements are more efficient than the and the part load requirements are less efficient. Uh, and so and then if you look at the other column, the part load's more efficient and the full load's less efficient. So we've given you the two columns, and most chillers will run at part load, but sometimes a chiller's built. Suppose you'll have a chiller you're going to base load with, and some other chillers that you're going to use in another way. So we give you the two columns so you can pick from. So that's the difference in the columns, part load use or full load use. Now, do 90.1 follow IECC or vice versa? What's the difference? So here's the way it works. And remember, I'm on 90.1, so this is my viewpoint. But 90.1 is set up to come in a year, almost 2 years before IECC. So we do that on purpose. So, our code dates are different than their code dates. Now, we have a committee that's whole, it's a working group, a subcommittee of the committees, but it's a committee that has people from all of our other committees on it, and they take our every change we make to our standard. They take it and put it in the forms and the wording and the way you have to do it to submit for change to the IECC. So we go to the IECC meetings and everything, and we try to get all the changes we make in 90.1 into the IECC. And that's so that we can run parallel to each other, and it'll be easy for people to use. Now, they make this whole big set of books, and authorities have jurisdiction. The local jurisdictions and stuff like to buy the set of books, and so they have an advantage on actually selling it to the code officials. So they are adopted in more places than we are, but because they have to be as efficient as we are or better, they always have inside the standard in the IECC, it says you can use our book or you can use 90.1 to comply with our standard. And so even if you're in a place that says, we've adopted the IECC, when you open the IECC, it'll say you can use 90.1. So you get that choice wherever you're at. Now, to decide which one to use, you have to look at your project and see if there's a hook, something bad for you on that project in one of the codes, and try to anticipate, well, I'm better off using the IECC because I'm going to have trouble complying with 90.1 on this requirement, or the vice versa. I'm better off using 90.1 because I'm going to have trouble with complying with this requirement. So you get the choice, even if the authority having jurisdiction says we're going to use the IECC. Now, if you're working on a federal building, like I do most of the time, federal buildings have adopted 90.1. That's in the law. So they have to meet the requirements of 90.1. So, that includes a lot of jurisdictions. Now, again, if you're doing less than 3 stories and you're in the residential type market, then actually the IECC has been adopted by the federal government for use on residential properties. So we have an ASHRAE 90.2 that does residential, but it is not the model code, and so it's not what is used in that. So that's the way it works. And So I would say that that we work to get everything into ACC. It comes out later than we do, and we try to make sure it meets the code. Now, recently, it's interesting because several people on our standard in our committees have started working on the IACC code, but it has a whole different process. And even the like our committees are responsible for writing the code. What we do is our subcommittees write the changes or the requirements. They go to the full committee. The full committee has to vote for them and has to vote for them to go out for public review. Then it comes to you for public review, and every person can make a comment on a change during public review. Now, it's simple. You go to our website, you go to a thing that says standards over the click. You don't have to be a member or anything. You click it, it takes you to a place that says, here are the changes being made in the standards. You can click one button on those changes for 90.1 for anything, and you can make a comment. Now, if you make a comment, you have to put a reason you don't think it should be done, or you do think it should be done. And then you have to put a little something technical so that we can look at it and say, this is reasonable, this is something the guy really thinks about or whatever. And then it's assigned to one of us, and we have to call you, and we actually have to resolve your comment before it can go into the standard. Now, if we talk to you several times, if we do our best, if we work to resolve you and you just will not be resolved, we can write it up and say, we are going forward with putting this in the standard with knowledge of unresolved commenters. That piece of paper has to go up to the standards, sometimes to the board of directors, but it has to be approved above us. They don't rewrite it. We don't ever get it rewritten or anything, but they send it back to us and say, try again, or they say, okay, or something happens. But we get to write the standard. Now, in IACC, I'm not sure how it happens, but it seems like that there's other ways that things get changed after the technical people fool with them. Anyway, that's the difference. We both have to claim to be a consensus standard, but we let the whole world consensus us, and the code officials have most of the sway. They're the ones that are voting, and it's changed a little bit. There's a different process for consensus in the IACC, but both of us, we work much closer together than we did in years past. And as you know, probably the 189, we still have a 189 committee. We write a standard 189, but we've made a deal with the IACC that they adopt that standard is the green standard that they use, the stretch standard. And so 189 is just, we don't publish it anymore. There's no ASHRAE 189 that you can buy. It is part of, or is the standard for the IACC green standard, the stretch standard. All right, any other questions? Thank you for your questions. I really like your questions, and it makes it more interesting to make sure that I'm answering what you need to know. All right. Let's see. So here's that table. You may have forgotten I was about ready to show you a table. This is a new table. It's a different way to approach this problem. So here's the climate zones. Here's the areas without exhaust energy recovery. Here's areas with exhaust energy recovery, because this changes how much energy you're using. And then this is occupant outdoor airflow components, CFM per 1,000 square feet. So if you have the requirement of 100 to 200 CFM, or 199 CFM per 100 square feet, this is from ASHRAE 62. If you look over there and it says, for this many people per 1,000 square feet, this is the CFM you need, and you know how many people you got. So you multiply it together and you get your CFM per thousand, and then you come down this table, and this is the area of the room. So if you've got between 100 and 109 CFM per thousand and you're in climate zone 2A, then your room could be 1100 CFM. If it was 1101, or if it's 1,099 square feet, you don't have to put demand control ventilation. If it's 1,100, you do. I hope I explained that. I understood it. Anyway, you can ask a question if that wasn't clear enough. All right. So miscellaneous changes to 6.4. So this is again, 6.4 is mandatory requirements. Walk-in coolers and freezers. There's a changed requirement for the doors to meet updated requirements. So, and then liquid to liquid heat exchangers. We've carried this empty table for liquid to liquid heat exchangers, section 6.8, and we've just removed it, and we've referenced AHR 412, which is some requirements for liquid heat exchangers. There was not a good way for us to build a table that we were happy with, ever get a consensus table. So, and then I'll talk a little bit about walk-in coolers and freezers. So what we did was we cannot change federal requirements. And the federal government has a program called Energy Star, which they rate the best appliances, even commercial appliances. And so what we did was, for our commercial appliance refrigeration requirements, we took Energy Star and we codified. So we made it where, if you can buy an Energy Star appliance or you not buy Energy Star appliance, and based on what the government put out. But what we did, we took that and we made it where you have to buy an Energy Star requirement to meet 90.1. So we codified the requirements out of Energy Star, stuck them in. But what it means is we can't change the wording of them because they're government requirements. So they're in, and they're, and it was a good thing because they're not required by the federal government. They're just something to know they're good. But if you're going to comply with 9.1, you have to use it. So I don't talk much about them because all I have to say to you is tell everybody to use an Energy Star, and then you'll be good. So we do have requirements for DX DOAS systems. These are dedicated outside air systems, 100% outside air. We worked very hard with the manufacturers to come up with this. This is the minimum efficiency requirements with energy recovery. And this is a coefficient of performance. And it's escaping me what this initial means, but what this means is it includes the humidity control in it and the energy recovery in it. So this is probably energy recovery and the stuff. So anyway, this was a big deal because it was hard for them to come up with a way to include energy recovery and the two machines working together, and then we wrote rules around it. So this is a good piece of paper and a good thing we did. So this started in 2016. I don't believe we updated the table since, but it is important to choose an efficient DOAS with energy recovery. And we do have a table without energy recovery also, but I didn't mention it because it did not change in 2016. HVAC systems, construction and insulation. So this is always in the mandatory section. It requires that you properly insulate and that the construction of the plenums and stuff meet the requirements. So we have for insulation, we have a general section, duct and plenum insulation, and we actually have tables for those, 682A and B. Piping insulation per tables. We have tables for that. It's also important, I'll show you the table in a minute, make it easier to explain. We also have that you have to insulate the back of a sensible heating panel so that you don't heat the ceiling, the room above you. And radiant floor heating, this is not the slab, but this is if you have a radiant floor like on the second floor or the third floor, you have to insulate again to keep it from heating the floor you don't want to be heating, if going down if you're on the second floor. Ducts and plenum leakage, all duct pressure class ratings shall be designated on the drawings, and duct leakage tests for over 3 inches of static. The ceiling has to be A to meet 90.1. SMACDA has ceiling classes. They allow A, B, and C, but to meet 90.1, you have to only use A. Minimum duct insulation values. So this is changed in 2016. The table did change. These are minimum values, so sometimes you can use, should use more than this. And they are sorted by exterior, unconditioned space, or buried ducts, indirectly conditioned space. Indirectly conditioned spaces are plenums and places like that. Now, these are your climate zones, and this is supply and return duct for heating and cooling. This is supply ducts for heating only. This is supply ducts for cooling only. And you can see that there's not much variation in the requirements, but there are some, and they are minimum requirements. Here's the one for piping. This is for hot pipe insulation. So this is the conductivity of the insulation. This is the mean rating for that insulation, so you'll know how hot it is. And this is the fluid temperature that it applies to as far as our code. So notice that we don't require insulation on a hot pipe that's cooler than 105 degrees. And then we require, based on the pipe size, we require a certain insulation thickness. And this equation is important. Fiberglass conductivity of 23 is kind of the center of what we've been using here. And if it is not 23, then you have to use this equation, which has an exponent in it. So I'm just warning you that that thickness of the insulation grows very quickly if you have conductivity that's worse than fiberglass. And this is the cold pipe insulation. And you'll notice that we don't require insulation on cold pipe warmer than 60 degrees, which means that if you've got pipe between 105 or less than 105, but more than 60, as far as the energy codes required, you don't have to insulate it. Now, this might not be a good idea in your building because that pipe could sweat. This really comes into return pipe and some condenser piping and stuff. But anyway, if you wanted to do it, you could meet the code without doing it, but you would take a chance that you would have some problems with sweating, etc. But the reason it's there is we could not justify the cost of insulating that pipe on a pure energy basis. The amount of heat we lost out of that pipe was not justified by cost to cause us to have to insulate. So this is the same kind of table, pretty much the same thicknesses and pipe. It runs the same way, has the same equation. So prescriptive section. Now we're going to move. The thing that's different in the mandatory section and prescriptive section is anything we're talking about that's a 6.5. If you do or the energy cost method or now the TSRP, then you can avoid all the prescriptive section. You can just say, I don't have to meet it because my model says I use less energy than a building built to comply with 9.1 prescriptive section. Now, we started off with economizers. Back in '99, we started off with economizers. Economizers are a way to save energy because you're not running the compressors and you're using the outside air to cool the building. Every system with a fan shall have either an air or water side economizer that's climate dependent requirements based on a bunch of, and back then they were DO2, DOE2 analysis is where we set all these requirements, but the now they're Energy Plus is are being used to to at this point they're all Energy Plus. Okay, so the requirement says that you have to size the outside air duct to handle the same amount of CFM as you're providing. So 100% of the CFM must be available to the economizer, and the duct must not be more restricted. Control off of the supply air temperature, not the mixed air temperature. So we want to supply off the same thing that you're supplying that you're controlling the compressor off of. We want to control off of. So if you're controlling the compressor off the room thermostat, we want to control the economizer off the room thermostat. If you're using a VAV system or something where you're using the air, the supply air temperature in the duct, we want to control the economizer off the supply air temperature in the duct. Now, both outdoor air and return air dampers shall meet the leakage requirements of the table for the normal louvers type dampers. The means must be provided to relieve excess air to prevent overpressurization. So you'll have to have some way to get that air out of there. So the building, you can shut the doors to the building and everything. Relief air outlet located to avoid recirculation. So this air that you let out of the building, we want to make sure you don't suck it right back in. So prescriptive sex, this is the economizers required. So in the warm climate zones, the warmest, 0A, 0B, 1A, and 1B, that's the hot, humid, hot, and dry. No economizers are required. So that's because the air we're going to bring in is going to be most of the time not usable, and so we don't require it because of the paybacks. Everything's based on payback. Now, in all the other climate zones, we require those economizers. And for 2022, we figured out that if a unit's outside, whether on the roof or sitting beside the building, it is cheaper to put an economizer in that unit. And so we have lowered to around 3 tons the requirement to add economizer. If the building's inside, if the unit's inside where you have to duct and do some stuff for that economizer, then we're still about 5 tons, 54,000, a little less than 5 tons. So that's new, lowering the threshold where you have to put an economizer. All right, eliminate, if you want to not put an economizer in, these are the numbers we think you're saving by using an economizer. So based on your climate zone, you have to show, like for 4A, you would have to say, you'd have to find a piece of equipment that was 42% more efficient than the piece of equipment we're showing in our tables to be able to eliminate the economizer, or 17% in a warm climate zone like 2A. So the colder the climate zone, the more often you can use economizers, and the harder it is to eliminate by equipment efficiency improvement. So this is the way you control the economizer, is by you have different choices. So fixed dry bulb temperature is one way to control it. And if you're doing that, then for the climate zones, this long list of climate zones, then you have to hold it in economizer until your outdoor air temperature is above 75 degrees, which is hotter than you would think. But remember, we use a compressor assisted economizer. So at a certain point, as long as we're putting the outside air first, we let the compressor come on to help us. But you're holding that damper 100% open, and you're using it with the economizer. All right. So then, if it's in 5A or 6A, which is in the middle of the country, we let you turn it off at 70 degrees. 1A through 4A, the hottest part of the deal, we let you turn it off at 65 degrees. These are dry, these are wet, so humidity has to do with that calculation and stuff. Differential dry bulb temperature. So this is comparing, this is fixed, this is comparing the outside air to the return air temperature differential. Outside air greater than return air. When that happens, when it gets to be greater than, you turn it off. A fixed enthalpy with fixed dry bulb temperature. So fixed enthalpy, we require you also to have the dry bulb, because enthalpy is not a reliable indicator. You can be in the desert and have real dry air, but very hot, and it would be, you would show lower enthalpy than some air that you would want to have in the building. So we also have to look at the dry bulb to make sure that's not happening. So we use the 28 BTUs per pound for your enthalpy, and we use your 75 degrees for your outside air. And you turn, this is always where you turn it off. And then the differential enthalpy with fixed dry bulb temperature. So this is again where your outside air enthalpy gets greater than your return air enthalpy, and your outside air temperature is greater than 75, then you turn that off. Now, there's a lot of debate about enthalpy in the standard, in the working groups, because enthalpy controllers that are good, give you good results consistently, are very expensive, and we can't afford to require them for the paybacks. But in real life, if you're using a lot of economizers and you're using enthalpy for a lot of your control loops, then you should at least once, and you can share it in some weather station or something, get a good enthalpy controller, which costs several $1,000s. Prescriptive requirements for the way we use reheat. So it's important. I told you that we do not allow you to heat and cool the same stream, but for VAV boxes we have an exemption. So we call this the dual set point, and that's the way we, since 2019, we require you to do it. So the deadband does not exceed the larger, here's the deadband, of 20%, this is the airflow, this is the height of 20% of design peak airflow, or that required by ASHRAE 62. Now, this gets a little complicated, and it's not really written down the way you would like it to. So this is well, let me see, I think I might do this better on the next one. All right, this will work. So what see this 20%, where it comes from is that the idea that you're in this deadband and you're in this area here, but you're actually sometimes here and most this way mostly, but you're modulating, and that there's a requirement in 62 that allows you to average your airflow, and by using that idea of averaging, that we did a lot of calculations, and we think with the averaging that 20% is the right answer. And so you can set 20%, even if it's less than ASHRAE 62, and you can say that you're modulating it back and forth, that you're not going to set it dead man, you're going to be going back and forth, and that the average will meet ASHRAE 62. Now, you know, that's up to you to design a record, but that's where this number came from. A bunch of tests, a bunch of the calculations that said 20% would meet ASHRAE 62 in a normal VAV box as it modulated the amount of air it was putting out, that it would meet their requirement for an averaging. So that's where this comes. So we advertised 20% as a good number to set to. Now, all right. So what happens is as the room cools down, you know, you'll supply an air, let's say at 55 degrees because that's standard, and your damper starts to close, and it gets down to the minimum set. Now your minimum set could be 20, it could be whatever you calculate at ASHRAE 62, but one of those numbers somewhere in there. This used to be 30 is what everybody would kind of set at, but we believe we can drive it down to 20. All right, and here's the second reason coming up. So then we go into deadband, and then we start to heat. So this would either turn on your electric heat or your hot water heat, and start to heat the building or start to heat the room. Now your box is as closed as it can be, and we're heating that airstream again. And that's the key, is we're allowing you to cool it down to 55 and then reheat it, but based on it flow being lower than it was when you cooled it. So then when you reach a maximum temperature that you're going to allow, and this is driven by, we'll go over it in a minute, but this is driven by, you know, ASHRAE 62 has a maximum of 15 degrees above the thermostat set point in the room, and 90.1 has one of 20 degrees above. But anyway, there's a maximum temperature allowed. And then the second stage of heat, because in case that's not enough, we let you open the damper back up. So the damper would open back up until you were putting a maximum of 50% of the airflow that you had over here through. So again, this is this kind of modulation stuff where we're hitting 20% at the low, but we're allowed to go up to 50 over here. And then sometimes it would get, that would need a little more cooling, so we go this direction. Anyway, so that's the way that works. And then suppose you were using a DOAS and you were supplying the air directly to the room from your DOAS, which is one of the ways they do it, and one of the ways actually I do a lot of defense work for the DoD, and the DoD pretty much requires you to use a DOAS directly to the room. So if that happens, then you can go to zero set with your normal VAV box because it doesn't have outside air in it at all. It's not controlling the outside air. So if you're going direct to space, you can go to zero set point on your box, since it's not required. And then you can come over to here to where you need heating, and then you can start opening back up. But you won't have to do this dead man at velocity or with flow. So the minimum primary airflow rate required to meet a simplified procedure ventilation requirement of ASHRAE 62. So ASHRAE 62 came out with a new simplified procedure. I think it was 2019, I think. And you can use that. So that when we adopted that, we eliminated a minimum set airflow and tied the airflow requirement to a new simplified approach procedure, ASHRAE 62. So the 20 is still available to you to think about, but we officially, that's what we mean by this ASHRAE 62 now, is ASHRAE 62 by the simplified procedure. And the simplified procedure won't, from what I can tell working on it, it is easier to use than the spreadsheet that they gave us. If you buy ASHRAE 62, you get a spreadsheet, and you can go through and you put more air in your spaces that are controlling how much percentage of outside air you get, so that then those no longer in control. That it's better to put more air in there than to open your outside air damper that wide, so you can eliminate those. This simplified procedure kind of removes that iterative approach, but your final answer is not quite as low as your possible final answer in the previous way. Overhead supply air temperature limited. So this is what I was talking about just a minute ago. For 90.1, if you were heating to 70, which would be high, then you could go to 90. 20 degrees difference between the thermostat and the supply. Now, why that is because first air flew from a ceiling diffuser likes to hug the ceiling. Then this air is hotter than the air of the room, so it likes to hug the ceiling. So it may not get down there and heat the room when the return is at the same level. If you move this return within 6 feet of the floor, then the requirement's off. You can do anything you want to with the heat, how hot it is. And in ASHRAE 62, it's only 15 degrees, so you would have to use 85. Now, we are finding that we can heat with much cooler air than we thought we could heat with. So that 85 number is not, outlandish. We're heating with, successfully heating with much cooler air. So when it first came out, it scared people to death, but it's turning out to be okay. Heating control. Preheat coils. Preheat coils must be off when mechanical cooling or economizer in operation. That makes sense. Ventilation of air heating control, new in 2016, and then we added an exception in 2022. Ventilation units operating with other heating and cooling systems shall not supply air above 60 degrees. When building load or outdoor air temperature indicate the majority of zones require cooling. For a community control series, energy recovery can be used. All right, so what we're saying here is if you do have a DOS supplying air directly to the room, we don't allow you to reheat it. So you cooled it down to 55, say, to get rid of all the humidity in it, maybe 53 or something even, but because you had a lot of humidity in that outside air and you had to get rid of it. So you got rid of it. We don't want you to reheat it, because we think that if you're supplying a small amount of the total amount of air to that room, that you can find a place to blow it where it won't blow directly on a person, maybe, but it will help if the building is in air conditioning mode anyway. We don't want you to throw away that cold air. We want you to use it instead of using the main system to cool that same air. So now, again, I do federal buildings all the time. This is not allowed in those federal buildings. They require us to reheat within 5 degrees of the room, but that's not their whole job is not saving energy. I think that's just the way they feel about it. All right. So now I'm going to tell you about about the motor. We have a requirement for only so much energy being used in the motor horsepower per CFM. So that we're limiting the amount of horsepower you can use in your fan systems. So the way it works is you'll have a supply fan. The supply fan is the fan that has a coil on it. It's the main fan. You'll have the CFM through the supply fan. All right, so this comes down and it goes through a VAV box. That doesn't use any energy, that's fine. Goes through a series fan powered box. This fan power uses energy at the same time you're at design condition. So you have to add this fan. So far you would add this fan to this fan. That's what we're talking about, horsepower. Then if you go down the duct and you go through a parallel fan powered box, this box only runs in heating, which is not considered design conditions. And so you don't have to count it. If you have a churning fan, say supplying a conference room, but the air does not leave the room, we don't require you to count that. If you have an exhaust fan that leaves the building, we require you to have that. So you would have to take this horsepower plus this horsepower, but this horsepower. And if you have a return fan that runs when the supply fan, in normal conditions, then you have to count it. So you would have this fan, this fan, this fan, this fan, all that horsepower adds together. If this was a relief fan that only runs in economizer mode or something, then you would not have to count it. Now, you take that horsepower. This is a constant volume. This is a variable volume system. This is option 1 when we're going to use the nameplate horsepower. You take that horsepower, you added it all up, and for a variable system, let's say, then your horsepower has to be less than the CFM through that main supply coil and fan times 0.0015. Constant volume is a little lower. Is a little lower than that 0.01. All right, so that's the allowable nameplate horsepower. Now, you do this every time because it's easy to do, and if you pass, you pass, and you're through. Now, if you didn't pass, you go down here and you run your brake horsepower. Now, your brake horsepower, you'll have to get it from the manufacturer or whatever for the piece of equipment. But your brake horsepower is less than or equal to, this one is 0.0013 because of your brake horsepower, same CFM, plus A. Now, what is A? A is some adjustments, and you only get them when you're doing option 2. So this is your adjustment. So if you have, exhaust filters, scrubbers, and other treatments, well, the pressure drop of the example. So if you're using filters, MERV filters 9 through 12, harder filters, or 13 through 15, you get adjustment. You get 0.5 inches of water column in adjustment, 0.9. You add up all your adjustments. You have a few that can give you if you didn't have a cooling coil, you would actually get a penalty. But you add up your adjustments, and then you come over here and you take your PD, which is your adjustments, and you take the CFM through each one of those items, not your total, but your what's through those items. And so then you multiply your adjustment times your CFM through the item, divided by 4131, and you get your A. So you can do that whatever, how many times you got, sum them up, you get your A, and you use that right there. So if that passes, your brake horsepower plus the A's plus that, then you can go forward. But you need to be careful because we've had several times when a manufacturer will send us a selection, and normally it's it's a little bit of the ductwork we've got on it, but there's tremendous. We're asking for smaller and smaller boxers with more and more stuff in them. There's tremendous internal pressure drop happening inside a lot of the units, and it's not their fault. We just have a lot of stuff, and we keep wanting to build a smaller room. Anyway, but if they send it to you and you design around it, and then you get to the end, now you can check these. The easiest way to check these is to put them into ComCheck again. Now, you don't have to be doing concept for compliance and to turn in, but you can always turn it on and run just these small sections. Like I told you, people run it for the envelope, they run it for the lighting, they run it for the envelope for those averaging, for those adjustments for the averaging for it. And then you can run it for this brake horsepower stuff. And just use that tool is part of it. Anyway, it'll show you if you pass or not as you enter this stuff. Now, but if you don't pass and you've told the architect how big the room is and all that other stuff, and you wait till the end of the job to run this calculation, you can embarrass yourself because you may have to go back to them and say, I need another foot to get to make this box bigger and fit and it works. So this is important to run kind of as soon as you get your selections, or actually to try to, I like to make people or ask the designers to get these selections early in the design process instead of putting it off till later. And so then as you get to the end with this brake horsepower, if your motor is greater than 6, if your motor is less than 6 brake horsepower, then you can use the motor you actually install can be 1.5 times that brake horsepower for your horsepower. If it's the other way, that's 1.3, and the first available motor that bigger than that number. So you get a little break there on how much horsepower you're putting in too. So there's a lot of advantage to option 2, but if you just qualify under option 1, then it's no use to go ahead. So if you're using a DOS system, suppose it supplies several rooms, and each one of those rooms have a percentage of the CFM. You have to put a percentage of the fan horsepower of the DOS into that space or into. So suppose the DOS is serving 2 different air handler systems. You have to or more. You have to percentage out that CFM between them and use that horsepower by that same percentage as the CFM. So it would just be another fan you added, just like you would your exhaust fan. Static pressure sensor location. We've always had this requirement of 2/3 down the duct. That's where we want you to control your VAV fans. Now, because we have the set point reset, we just say the VAV sensor controlling fan must be located such that its set point is less than or equal to 1.2 inches of water column. Now, this is a made up number. It doesn't make any sense. It's just that you have to have some place to start, and it's a place to start, because what you have to do after that is for systems with digital control at zone level, set point must be reset based on zone requiring the greatest pressure. The set point is reset lower until one zone damper is nearly wide open. So what this means is that your digital controls are looking at each damper in each one of your VAV boxes. And if one damper is all the way open and still cannot satisfy the space, then you have to speed up the fan. If none of your dampers are fully open, then you can keep slowing down your fan. So your sequence of operations has to talk about, if no dampers are fully open, my fan keeps slowing down until one is 100% open, and then it has to start speeding back up. Now, you always have to go back to this VAV sensor controlling the fan must be located, because what we're talking about resetting, where we're talking about, the damper is not fully open, so you're going to you can keep speeding the fan up. What we really mean is you go back to that sensor and you lower. Let's say you would lower the static pressure requirement so that the fan would speed up no, you would raise it. You would raise the allowed static pressure so it would speed up to meet that new static pressure. And then, but you never control the fan from the VAV damper. That would be terrible. It would be way complicated. It wouldn't work properly. You control the set point on that sensor from your VAV dampers. And then that set point controls your fan. And that way the fan's not going to run all over the place chasing those dampers. All right. So here's an example of the old-fashioned way we did it before we started doing this, and why it's a problem is the balancing contractor set this fan. This is an actual fan. This is the trend data for static set point of 0.75. That's the static set point. Total design for the whole system, internal and external, was 4.8. Anyway, so you can see the fan starts up, it runs up here, and then it hits this speed, and then it works back and forth and back and forth and back and forth based on that static pressure sensor. But the problem is it was designed, we said we're going to save energy down to 30%. This fan can run at 30% design, but because of where it was set, it will never slow down more than 53, 54%. But if you had this reset system and no damper ever opened, it would go down to the 30%. So that's why it's important to allow it to go down as low as it can to get as much energy savings from that variable speed drive as we can. So in 2019, we were looking at fan arrays because they're popular, and we said that it must have a fan FEI of 1 or higher. Each fan and fan array uses a variable air volume system for a variable fan volume system that meets the requirement of the sections on FEI shall be 0.95 or bigger. FEI shall be calculated in accordance with AMCA 808. So this is modified in 2019, as I told you. I'm just running, I'm trying to keep it to 16, 19, and 22. So it really, you lost a little background here. But anyway, the FEI is, you should be able to get it in from every manufacturer in the fan tables. And they'll give you the FEI and you just have to pick it. They know, they'll warn you. Normally I see warnings now that says this didn't meet the FEI or something. FEI is a rating standard that was developed by AMCA, and they sold it to us and DOE. Return and relief fan control. So this is for 2016, and we had what we believe to be a problem in building pressurization, in that designers were using all kinds of methods to pressurize a building, and some of them were quite energy efficient. You know, where they put the sensors, what they were up to, and you know what happens on building pressurization is you're bringing in more outside air, and when you bring in more outside air, it draws our attention because that outside air needs to be cooled or dehumidified, and it costs energy. So we're trying to minimize the amount of outside air you have to bring in for pressurization, and so we require that you use fan tracking. Return and relief fan shall comply with the following. And what this says is that you're going to track, your return fan is going to track with an offset your return air fan. Return air fan will have an offset. It'll be running slower or moving less air than your supply fan. And then your exhaust fan is going to be taking what it needs to take out to pressurize the building, but you're going to do it by tracking. And the tracking is really the return fan on your supply air fan. And we require you to give some, you know, the balance contractor can set up at the end, but we require you to give some information on that offset. Parallel flow, if you used parallel flow fan powered VAV boxes, and at night, generally when we're in setback, but anytime that the building says Well, it is not. It says during unoccupied periods. That's right. So at night, building's unoccupied, you've gone into setback, there's no heating or cooling on, and all of a sudden it gets cold enough in the building that we need some heat. So first thing you're going to do is turn on that box, and you're going to turn on the unit and that box, and the unit's going to supply air to that box, and it's going to be cold, but the box will heat it. And you do that until you get several boxes that are running, and at some point you can decide, okay, I'll switch over and turn on the main heat at the unit. We're trying to eliminate, suppose it's just one perimeter area on the north side that needs heat. We're trying to keep from heating that whole floor. Dehumidification control interaction. The So this is new for 2019, and so this is for the hot climate zones, hot and moist climate zones. 0A, 1A, 2A, and 3A. The system shall be designed to allow supply air temperature reset while the dehumidification is provided. When dehumidification control is active, air economizers shall be locked out. So, you've got a DX unit, you've got a unit, and you're saying, I'm in dehumidification mode. So the supplier temperature has to be higher and reheat is not allowed. Some ways this can be done in cooling or outside air with a differential cooling coil, then mixing with return air, bypassing some return around the coil, using a wraparound coil or something else. But the thing that was happened is that we never had these zones have to do supply air temperature reset. Always these were excluded. OA, 1A, 2A, and 3A. I live in 2A. So I did not vote for this, but we have to control humidity. And so a lot of times we have a dehumidification cycle that cools and heats. Some we always meet the requirements of the code, but the thing that helped us is we didn't have to reset. So if we get in, and it's the things that cause us the most trouble. So you get in this area where the temperature is nice outside, and you don't have to run as much air conditioning, and you go to this reset mode. Well, I can supply, instead of 55-degree air, I can supply 58-degree air, 60-degree air, or some number that'll still cool the space because it's not hot outside. But the fall, the shoulder months, the fall and the spring are the most terrible humidity, because your unit doesn't run and it's really high humidity outside in these climate zones, 2A, for example. And so it's terrible, because if you don't have some way to go into dehumidification cycle, you will cause humidity problems in the building. Humidity problems cause mold problems. Mold problems causes the building to fall down. So it's a horrible thing to do. But anyway, there are a lot of people from the cold part of the country in California on the committee. So even if some of us voted against it, this is part of the standard. So the supply temperature has to be higher and reheat is not allowed. And this is what they went through to say why we shouldn't care, because we can mix some, we can cool some air, and we can, just like for a VAV type system, we can cool some of the air, right, and then we can heat it and mix it back. We can do some stuff. We can do a wraparound coil. Now, that works, but on a hot gas wraparound, you can't control the temperature you're going to come off on. Anyway, so it's a problem, but it passed, it got in, and it's something you have to do. And it's fair, it's new, it finally got in 2019. Now, I'll just tell you a story that I was doing hospital work for a while, and I bought the best unit you can buy, to control humidity, and second best. It wasn't custom or anything, but that you could afford and apply. Anyway, so when an operating room in the fall or the spring gets out of humidity, uh, the humidity set point gets off, alarm goes off, they can't operate in that room until that humidity's back where it's supposed to be. And you know who gets the call, right? It's me. I get the call. It says, we can't operate, and there's a guy over here with a bullet in his stomach. What do you want to do? You know, this is a bad call to get, right? So you have to be very careful with these systems. And luckily there's a guy from Texas, from Houston, Texas, on the committee, that MD Anderson, that works hard to make sure that in hospitals where there's some exceptions and some things that'll help with this. But anyway, it's serious business. Uh, lower power fans that are not covered by section 6536 and having a fan nameplate electrical input power of less than 108 watts, or having a motor nameplate horsepower of less than 112 horsepower, shall meet the fan efficacy requirements of this table. Here's a fan efficacy. Now, these are small fans. These are little fans, and they're not going to move your needle at all in your building problem. But there's a whole lot of them in the world, and the people that are involved with these small fans, put this forward as a change to the standard. And it does save some energy, but it's just, it's really little numbers per fan or per your job problem. But there they are. Ventilation design. The outdoor air design should be based on ASHRAE 62 or 170 or a standard code. 170 is the hospital code. The design must limit outside air to no more than 130% of the calculated outside air. Now, or the design which can return, or you can set it up so that the controls can return to the required outside air with a single set point adjustment, or the system includes exhaust energy recovery. So what this is about is, green buildings has, and it was very popular for a while, has a thing to that you get a point for putting more than 130% of the required outside air into the space or into the system. And this point was causing more energy to be used. So we'll let you do it, but we want you to be able, if there's more energy used, or if you start having other problems, we want the control system to be able to go back to the required setting at just one, easily. Occupied standby controls. Zones serving, this is an interesting one, a good one. Zones serving only rooms that are required to have automatic partial off or automatically full off lighting controls. So we could only pay for it if we used the lighting controls. We only have 15 minutes left, but we're in great shape. Don't worry about a thing. That are only required to use lighting controls. So we needed a lighting controller to pay this back. So if you've got the lighting controllers in there, and they're going to send a signal to say this room is not occupied, within 5 minutes of it being unoccupied, you have to reset the dead band up 1 degree or down 1 degree, whether you're in heating or cooling. Now, when you're in dead band, you can go to zero set point if this space is listed with it in the 62.1 ASHRAE. There's tables. I think they've done what they've done it a little different now, but they used to have asterisks, and they have the same information. But anyway, it'll say these spaces are allowed to go to zero set point when unoccupied. And we work together with them, and they don't care about the carpet laying on the floor. It's based on occupancy, not, you can shut it completely off, because we debated it a long time with them. So that box can go to zero set when it's in dead band between those numbers. Now, we only required you to go -1 or +1 because we wanted this, we had to get this adopted. But, as the designer of record, and your customer, what happens is they come back into the room, and the system starts back up, and it takes a minute or two to get back to set point. So you can say, well, my people could stand 3 degrees or 4 degrees or something. It doesn't have to be just 1 degree in the dead band, and they would still be happy, and you can save more and more energy. So this is an individual box serving whatever it's serving, individual zone. So and then in 2022, we added reset the zone outdoor requirement to 0 for all zones in occupied standby mode. So it's the same thing, but what this means is that well, it just says you can close it. It says you can close it, and that you can tell the control system to back off of the amount of outside air required in that building. But if you slow down the fans, it's it's okay. But we added that you can reset the permit to 0 for that space. All right. Now, hydraulic. We're going to move from the air side to the water side, and the variable flow required for this system. So now, to have to put a variable flow in there, you have to have more than 3 control valves. So you have to have something that's going to be able to vary the flow. 30% of the design wattage at 50% of the flow for pump sizes per this table. So what we've always come up with is that a variable speed drive will lower the wattage to 30% at 50% of the flow. You can use something else on pumps. We haven't, only a vane axial fan that we find that would work like that on a fan, but for pumps there are some other things. But anyway, with the cost of variable speed drives, there's probably no debate. Modulate to 25% or minimum allowed by the manufacturer. So the pump goes down that far if it can. Controlled as a function of flow or pressure differential at the end of the system with a set point not more than 110% of critical circuit pressure drop and DDC set point reset. So in another part of the standard, we required you to turn into the authority having jurisdiction your calculation of your critical circuit pressure drop for this pump. So we do not want you to oversize that pump more than 10% above the critical, what you calculated for that path, or with DDC function of valve position. So we do, the DDC system, the DDC system of valve position is exactly what I talked about for the air side. So you look at the valves, you look at the position of the valves, and that once you set the pressure differential at the end, that pressure differential will be reset as the valves move. If no valve's full open, the pump will keep speeding up. If one valve is full open, if it's full open, they'll speed up. If it's not full open, they'll slow down. Variable speed not required if 50% of the heat is from electric boilers. This is because it's a problem. You don't want to burn up an electric boiler. On primary pumps in primary secondary systems and in the coil pump for freeze protection or heat recovery coil. Pump flow control. So this table was added in 2016, and before we had, just a regular thing saying this is the motor horsepower, and it was for the whole country. Now we do it by climate zone. So here's your chill water pumps in these climate zones. So at 2 horsepower in the hottest climate zones, you have to use a VFD, or you have to use a speed control pump. Now, You do not have to use it. None required in these climate zones at all for the for for this is the heating, that's the chill water. So you go through the warm zones, it gets higher and higher on the heat on the pumps till chilling air conditioning in Alaska, you can go up to 15 horsepower before you need it. Now, the climate zones for heating in 7 and 8, it's 5 horsepower, and then as we go down to the hottest zones, you don't have to put a VFD on the heating side until you're at 200 horsepower, so pretty high. The chill water cooling coil Delta T, chill water coil selection. So this is to me, this was an interesting one, 2016. We ran a bunch of models, and it's hard to say exactly because how far you pump into your coil, what's your fan pressure, but we did the best we could, and we arrived at a Delta T through the coil of 15. Now this is you have to design your system, a new system. We have some down there. You'll see we have some exclusions, but a new system has to be designed to at least have a 15-degree Delta T across the coil with leaving water temperature a minimum of 57 degrees, which means that you cannot supply, 15 from 57 is 42 degree water. So 42 degree water would be your coldest water you could supply. 42 degree water plus 15 is 57. If you use 44 degree water, you'd be fine. But if you use 41 degree water, you'd have to use 16 degree Delta T. So anyway, that's what we did. We came up, this was looking at the chillers, the cooling towers, the pumps, and the fans, and minimizing all those put together. We said 15 degrees was the right number to do that, or the minimum number to do that. You can go larger and probably maybe, but then your chiller may have to work harder. So we are, really getting into your business there, and sometimes I don't like that, but it was something that passed everybody, and it's okay. Building with high capacity space heating gas boiler systems. So this is for the heating water. This is not, we're not to service water heating yet. New buildings with gas water heater boiler systems that total more than 1 million BTUs, but not more than 10 million, shall comply with these exceptions. And these exceptions, these sections are coming up on the next slide, and some exceptions, but the boiler efficiency should be of 90%. So that means that you're going to use condensing boilers, and your hot water distribution system will return the water to the boiler at no hotter than 120 degrees. And if it operates, the water temperature entering the boiler is 140 or less, if the flow rate of the supply water temperature that recirculates directly to the return system, such that by three-way valves, you'll do that with you'll return through the three-way valves no greater than 20% of the design to flow to the operating boilers. So that means that, you send out 140 degree water and you bypass it all, it's going to be tough to get 120 back. So we have to limit that. If condensing temperatures, condensing boilers don't condense at more than 120 degrees. You're better off if you can get it back at about 100 degrees. You'll get a lot more use out of that boiler as far as savings. But and also, some of these numbers you have to be careful. We are an energy code, and so we don't prime ourselves on it, but we are aware that there's such a thing as Legionnaire's disease. So uh, we, yeah, I'm going to have just a few minutes to look and see if we have any. Since I may not even get, I might have gone too far. What is the difference? We did that one. Follow the EC. Thanks. The compliance for any compliance for heat recovery chiller. We'll handle that tomorrow. Um, I don't think so. I don't think so, but we'll have it tomorrow. There will be in the 2025 standard. The one we're working on now, definitely. But I don't think anything was in on the 2022 standard. So it's coming the next round, but it's not in yet. I'll talk about that tomorrow. For the zone minimum flow control, is there an exception for a lab with uh, or other similar situation? Lab with pressurization. Uh, exhaust requirements for other. Yes, well, let's make sure that I'm answering the right question because the flow control. Uh, which one of that is zone minimum flow control? Is that the horsepower thing? I can't decide what flow control might mean. Zone minimum flow control. Is there an exception? Well, maybe we can talk. If you can unmute, you can ask me direct, because I'm not quite getting your question out. But if your question is if there's exception for a lab with pressurization and exhaust require. Oh, is that the tracking? Sure. So we do allow, and I usually have a slide on it. What the labs. We know that the lab has to be probably negative to the hall, and we do allow those those type of systems where you got the hood that's varying, and you've got maybe other things, and you have that requirement that you're measuring your exhausts and your supply, making sure that you don't push things out in the corridor and all. Yes, all those are allowed inside the code. And like I said, before 2022, I did have a slide on showing that. I might have one that comes up later, but I doubt it. But anyway, yes, those are allowed as exceptions and pressurization. And also the added pressure drop through those lab equipment is allowed for fan horsepower and stuff. All right, so that's where we stop today. And I hope that this was useful to you. If you think of any questions, you can enter them when we first start tomorrow. We'll be back at the same time, and we're in good shape for finishing. So appreciate your being with me today, and I hope you've got something out of it. Thank you very much. See you tomorrow.